Picture this. You step into an elevator, press a button, and within seconds you're moving through a building as if gravity has been negotiated, politely, for your convenience. Most of us treat elevators like background noise. They're there when we need them, and if they're slow, we complain. But elevators are one of the most complex everyday systems in modern life. They blend mechanical engineering, computer logic, safety design, and human behavior. And as cities grow taller, elevators are quietly becoming the bloodstream of urban life. Today, we're going to explore the secret life of building elevators, how they decide where to go, why they sometimes stop at every floor except yours, what safety systems you never notice, and how new designs are reshaping the idea of what a building can be. Let's start with a basic question that turns out to be surprisingly deep. When you press an elevator button, what exactly are you asking the elevator to do? In older systems, you're basically placing a request into a queue. The elevator car is already on a route, and your floor gets added to the list. If the car is going up, it will usually keep going up and handle requests in that direction before coming down again. This is why you can get stuck in that classic situation. You're going down, but the elevator arrives going up, already full, as if it's personally determined to ignore you. But modern buildings often have multiple elevator cars that share the workload. Now the problem becomes less like follow a simple queue and more like coordinate a team under pressure. Engineers call this dispatching, deciding which car should answer which call. At first, dispatching sounds like an obvious task. Just send the nearest elevator, right? But nearest is a tricky concept. The closest car might be full or moving in the wrong direction or about to stop at many floors. Sometimes it's faster to send a slightly farther car that can take you directly. This is where elevator control systems start to look like a kind of real-world algorithm. The system tries to minimize average waiting time, reduce crowding, and keep traffic flowing. During rush hour, it may behave differently than at midday. In some buildings, the system even predicts patterns. It learns that at 8:45 a.m., people flood the lobby and go up. At 5:30 p.m., the flow reverses. After lunch, traffic scatters more randomly. You've probably noticed a newer style of elevator interface in some offices or hotels. You don't press a button inside the elevator at all. Instead, you enter your destination on a screen in the lobby, and it assigns you a letter or a specific car. This is called destination control. It changes the logic of the whole experience. Instead of collecting people in a car and then discovering where they want to go, the system knows everyone's destinations before they enter. That means it can group passengers heading to similar floors and reduce the number of stops. From a passenger's perspective, destination control can feel strange at first. It requires trust. You have to believe that the system's assigned car really will take you efficiently, even if it doesn't look like the closest one. But in many high-rise buildings, it makes a dramatic difference. Fewer stops means faster trips, and faster trips mean the building can function without needing an absurd number of elevator shafts. And elevator shafts matter more than you might think. In a tall building, the space taken up by elevators can become enormous. If you simply scale up a small building design to a skyscraper, you might end up dedicating a huge percentage of the floor plan to vertical transport. That's not only expensive, it also reduces usable space for apartments, offices, or public areas. So engineers use strategies to move people efficiently without turning the building into a bundle of empty tubes. One classic strategy is zoning. Elevators are assigned to certain ranges of floors. For example, one group serves floors 1 to 20, another group serves 21 to 40, and so on. This reduces the number of stops per elevator because each car focuses on a segment of the building. Another strategy is the sky lobby. You take an express elevator to a mid-level transfer floor, like an airport hub, then switch to local elevators that serve higher floors. This is common in super tall buildings because it reduces the number of shafts that must run all the way from the ground to the top. If that sounds inconvenient, think of it as the difference between a direct bus that stops everywhere and a subway system with express lines. Transfers can feel annoying, but they make it possible for the whole system to handle more passengers. Now, let's talk about something we rarely think about unless something goes wrong: safety. Elevators have a reputation for being safe, and statistically they are. But they're safe for a reason. They're packed with redundant systems, mechanical brakes, sensors, and strict regulations. A common fear is that an elevator will fall. Movies love this scenario. Reality is much less dramatic. Modern elevators have multiple layers of protection. First, the hoisting cables themselves are extremely strong, with large safety margins. And they're not just one cable. There are typically several steel cables or belts, so the failure of one doesn't mean total failure. Second, there's the braking system. If the elevator moves too fast, a governor mechanism detects the overspeed condition and triggers safety brakes that clamp onto the guide rails. This is like a last resort grip that stops the car from accelerating downward. Third, there are buffers at the bottom of the shaft, designed to absorb impact if a car ever reached the end of its travel path. But safety isn't only about dramatic falls. It's also about doors, sensors, and human behavior. Door systems are surprisingly sophisticated. They use light curtains, pressure sensors, and timing logic to prevent closing on passengers. Still, a lot of accidents happen not because the elevator fails, but because people try to beat the doors, rush into a closing gap, or hold doors open in unsafe ways. There's also the issue of leveling. The elevator must align with the floor. If it stops slightly above or below, it creates a trip hazard. So elevators constantly adjust their position and use sensors to ensure accurate stops. And then there's maintenance. Elevators are inspected regularly, and the best systems are monitored continuously. Some modern elevator companies use remote diagnostics. The elevator sends data about motor temperature, door cycle counts, vibration patterns, and error events. That means technicians can detect problems before passengers notice anything. So, if elevators are such a carefully engineered system, why do they still feel slow sometimes? Part of the answer is physics. The taller the building, the more time you spend accelerating and decelerating. An elevator can't instantly jump to top speed without making passengers uncomfortable. If acceleration is too strong, people feel lightheaded, their stomach drops, and the ride becomes unpleasant. Engineers balance speed with comfort. In very tall buildings, elevators can go extremely fast, but the experience can include ear pressure changes. Some super tall elevators even have systems to manage air pressure inside the cabin to reduce discomfort. Another reason elevators feel slow is social reality. People move unpredictably. They hesitate at doors, change their minds, carry large items, or press the wrong button. Every small delay multiplies when dozens of passengers pass through the system. Now, let's shift from the present to the near future, because elevator technology is changing in ways that could reshape architecture. One major innovation is the move from traditional steel cables to lighter materials. Some systems use coated steel belts, and others explore carbon fiber or advanced composites. Lighter materials reduce the weight the motor must move, which improves efficiency and allows taller buildings without massive cables. Then there's the concept that sounds almost impossible the first time you hear it: elevators that can move horizontally. A few experimental systems use magnetic propulsion, similar to maglev trains. Instead of a single cable pulling a car up and down, multiple cars can move through a loop of shafts, potentially traveling vertically and horizontally. In theory, this could turn a building into a three-dimensional transit network. Imagine an office complex where an elevator could take you up 10 floors and then slide sideways to another tower without you stepping out. This is not common yet, but the idea challenges a basic assumption: that elevators must be vertical. If that assumption changes, buildings could be designed more like connected neighborhoods in the air. Architects could create clusters of towers linked by shared elevator networks, distributing crowds more intelligently. But even without horizontal travel, the vertical city is already changing. Residential towers often include mixed-use floors: apartments, gyms, co-working spaces, clinics, cafes. The elevator becomes a public corridor, the place where different parts of your daily life connect. That leads to a subtle cultural point. Elevator design shapes behavior. In some cultures, elevators are quiet and formal. In others, small talk is normal. In some buildings, people avoid eye contact and stare at the floor numbers like it's an unspoken agreement. Elevator etiquette varies, but the design influences it. Mirrors can reduce claustrophobia and also make people feel observed, which changes behavior. Music can reduce awkward silence. Lighting and ceiling height can make a cabin feel larger or smaller. Even the placement of buttons affects passenger flow. If the panel is too close to the door, people cluster and block entry. If it's too far, people hesitate and the door stays open longer. These tiny details shape how smoothly crowds move. There's also accessibility. Elevators are a lifeline for people with mobility challenges, parents with strollers, travelers with luggage, and anyone recovering from injury. Features like audible floor announcements, braille buttons, and adequate cabin space are not luxuries. They're essential for making buildings usable by everyone. Now let's end with a question that sounds philosophical but is actually practical. What does an elevator represent in a modern city? On one level, it's a machine that moves people. But on another level, it's a system of fairness and access. If an elevator is unreliable, a building becomes less livable for people who can't use stairs. If a building's elevators are poorly planned, you waste time every day in lines and crowded lobbies. Elevators also determine how high we can build. Without them, skyscrapers would be architectural fantasies. And as cities face land scarcity and growing populations, the ability to move people efficiently upward becomes a major factor in urban planning. So, next time you step into an elevator, take a second to notice the quiet choreography at work. The algorithm that assigned your car, the sensors that keep the doors safe, the motors calibrated for comfort, and the entire building designed around the flow of human movement. It's not just a box that goes up and down. It's the hidden infrastructure that makes vertical life possible. Thanks for listening to Kuma English Listening Hub. If you'd like, listen again and focus on the key terms like dispatching, destination control, zoning, and redundancy. The more you replay and shadow the phrases, the more natural this kind of advanced real-world English will feel.